Hello everyone. Here we will see in this video another application of the Ampere Circuital Law, where we will be calculating an expression for the magnetic field inside a solenoid. I hope you know solenoid. Solenoid we can consider as to be a coil of having many number of turns, and when current passes through this solenoid, it behaves as a magnet. So we will be discussing that, and we will find an expression for the magnetic field inside the solenoid. So let us see how it can be done. We consider a long solenoid here. You can see the turns of the solenoid as shown here. This portion shows that the current is upward, in the upward direction from the plane of the paper, and whereas this portion shows that the current is moving in the inward direction to the plane of the paper. So if we consider the plane of the paper as the cross section which cuts through the solenoid lengthwise, then if we see the solenoid from one side, suppose we consider this side, if we see through this side, then the direction of current will be such that it appears to be the clockwise direction. This phase will behave as the south pole. Whereas if we see through this side, we will find that the direction of current is in the anti-clockwise direction. It behaves as the north pole. Actually, when we consider a solenoid, it consists of many turns, and each turn behave as a magnet. Its left phase behaving as the south pole, and the right one behaves at the north pole. And when we consider the whole solenoid, it is a combined effect of all the small magnets. So we get a large magnet here, and it depends on the value of current which passes through the solenoid. We have shown here, since it is a magnet, it has a south pole as well as north pole. The lines here drawn here, this shows the magnetic lines of force which passes through the solenoid. It will be even more clear from the second diagram which we are going to see now. See, look at the diagram here. These points are the points where the current is coming outwards from the plane surface of the paper. So these are shown by dots, whereas these are the points where the current enters the plane of the sheet. So these are shown by cross sign. Now the lines which are drawn here, these are the magnetic lines of force due to this current carrying conductor. We can say current carrying solenoid. And you can see through the solenoid, these are the lines which passes through the solenoid. So this represents the magnetic field inside the solenoid. What we are going to do is we are going to find an expression for the magnetic field inside the solenoid. So let us see how it is done. But before actually going to find the expression for the magnetic field inside the solenoid, let us first discuss one very simple thing, that whenever current flows through the solenoid, we can find the direction of the north pole and south pole of the solenoid. How it is done is, the direction of current, if you hold the solenoid in your right hand such that the curved finger represents the direction of current, then the thumb will point towards the north pole. This is Ampere's right hand rule. We are using right hand rule in many situations. This is one situation where we hold the solenoid such that the curved finger represents the direction of current, then the thumb will represent the direction of the north pole. The example can be taken here itself. You can see, if you consider the solenoid here, the curved fingers should be like this. So the thumb represents the direction of the north. So you see here the north is here, which is given by the Ampere's right hand rule. So this is a simple method to identify which direction or which side of the solenoid, which end of the solenoid will be the north pole and which one will be the south pole. Okay, Now we have taken a cross section of the solenoid lengthwise in the plane of the paper, where the dots here, you can see the dots here, the dots here represents the current is coming out of the plane of the paper, where the cross shows that the current is moving inside the plane of the paper. Dot represents outward direction and cross represents the inward direction, right? Now what we are going to do is find the magnetic field somewhere inside the solenoid. You can consider any point inside the solenoid. So for that we have to use the Ampere Circuital Law, and we all know to use Ampere Circuital Law we need a closed loop which is known as Amperian loop. So let us take a closed loop here given by A, B, C and D. So this is a closed loop in the shape of a rectangle here, but it doesn't matter whether it is in the shape of a rectangle or a square. So we have to take a loop, closed loop we have already taken. Now we will use the Ampere Circuital Law to find the magnetic field inside the solenoid. Somewhere here we are going to find the magnetic field, right? So let us see how it is done. Now the basic formula of the Ampere Circuital Law is integration B dot dl over a closed surface, over a closed loop is equal to mu naught times the total current threading the loop. Now we have seen here the loop is A, B, C, D, and you can see the dots coming out there. That is the current is coming out or passing through the loop. Now the value of current through the solenoid is I. So one time if it loops or if it passes through the Amperian loop, so the current will be I. If it is 2 times, then it is 2I. For 10 times it will be 10I. So we have to calculate the number of times it actually threads the loop, and then we have to multiply it with I to get the total current. So the formula we have to calculate. So what we will do is we will first take the left hand side, that is integration B dot dl over the closed loop, and we will solve it first and then we will equate it with the right hand side. So integration B dot dl over the closed loop A, B, C, D. Now this closed loop has 3 portions, A, B, B, C, C, D and D A. So accordingly integration is taken B dot dl over from A to B, then from B to C, C to D and D to A. So we are not using the closed loop here. That's why the circle symbol is not there, because these are not the closed loops. Now see the second term here, integration B dot dl from B to C. This is B and this is C. Now dl is in this direction from B to C, and the magnetic field B, you can see here, we have shown it earlier also, it is from the left side to the right side inside the solenoid. So they make an angle of 90 degree here. If let me draw it here so that you can understand it more clearly. The magnetic field is in this direction, okay, and dl is in this direction. So they make an angle of 90 degree, and cos 90 is 0. So here B dot dl will be 0 in the condition where we integrate the length from B to C. Now same is the case from D to A also. If we consider from D to A, the length dl is in this direction and the magnetic field is in this direction. They also make an angle of 90 degree here. So they cos 90 is 0. So integration B dot dl. That means the second term and the fourth term, they cancels out, and we are left out with the first and the third. Now let us check the third one. In the third one, integration B dot dl, actually in this region which is very near to the solenoid, but outside it, the magnetic field itself is 0, because the magnetic lines which come out of it will move through it, but it will not move so closer. So magnetic field itself is 0. So integration B dot dl, that is the third term from C to D. From C to D, it is 0 because the magnetic field itself is 0. So the third term also is 0. So we are left out with only the first term here. So integration b dot dl will be equal to integration b dot dl from a to b only. That is, this portion we have to consider. Now in this portion you can see dl and b both are in the same direction. So the angle between them is 0. So therefore integration b dot dl from a to b will be integration b dl cos 0 degree. So cos 0 degree is 1. So we will apply the Ampere's circuital law here. So we are left out with the first term, which is integration b dot dl for this region, which we know as the direction of magnetic field and the direction of dl both are same from a to b. So b dl cos 0 is 1. So b comes out integration dl. Now from a to b, the length already here is mentioned as L. So we write integration dl to be L. So we are getting the result here BL. Integration, that is the left hand side of the Ampere Circuital Law, mathematically is given by BL here. Right? Okay. Now we will consider the left hand side. Now it is in the left hand side, it is mu naught I, where I is the total current which is threading the loop. Threading the loop means the loop ABCD we have considered. So in this loop, the number of times the turn is passing through the loop multiplied by the current will give you the total current threading the loop. So we need to first calculate the number of turns which are threading the loop. So for this, there is a number n we have considered, which is the number of turns per unit length. That is, for the unit length of the solenoid here, this is the length of the solenoid. For the unit length of the solenoid, the number of turns is small n. So for L length, we know from A to B the length is L. So for L length, the number of turns which passes through the loop is n into L. This is given by n into L. So we have the total number of turns which are threading the loop. So naturally the total current which is passing through the loop will be multiplied by I. NL is the total number of turns, and multiplied by I give the total current threading the loop. So mu naught, the left hand side is BL, which we have calculated, and the right hand side, which is mu naught into total current threading the loop, will be mu naught into NLI, where the right hand side we have already mentioned. We have put this value, the right hand side we have put this value here, and the left hand side we have put this value BL, and the right hand side, which is mu naught I, the value of I we have calculated here. We put the value of I here. So finally we get the result, which is B is equal to mu naught Ni. So I hope this is very clear to you. Now see here, in this solenoid, the magnetic field at the end of the solenoid, that is in this region or in this region, it is half of the value which we have calculated, that is half of B mu naught Ni. And graphically we can also show it. You can see here, from the center of the solenoid, if we move from the either side, the value always remains B, which is mu naught Ni. But as we reach the end, the value becomes half, which is 1 by 2 mu naught Ni. So at the ends, you remember, the value is half of the value which is there at the center or the middle region. I hope this is very clear to you. Any doubt, you can post me the doubts. Thank you.